Hi, everybody.
Hi.
The plan for today is we're going to finish up chapter 9. And then I'm going to give you guys your take-home chapter 9 quiz. That's your virtual day assignment for Friday, maybe technically the day, although you can do it whenever you want, because it's take-home. So in chapter 9, we've been talking about this idea about the derivative. We've talked about that the derivative is really like the same thing as the instantaneous rate of change, or the slope of the line tangent to a curve at a point. That those three things are kind of talking all about the same thing. We'll talk about how to find the derivative algebraically using our derivative rules, specifically the power rule, and then some algebra to get things into a form where we can do that. And then we've talked about how, since the derivative is telling us about slope, we can use the derivative to tell us about features of its original function. So by looking at where the derivative is positive and negative, I can tell where the function f was increasing or decreasing. And since I know where f is increasing and decreasing, I can tell where f finds an extrema, a local minimum or maximum. And if I look at the second derivative, and I look at where that's positive and negative, that can tell me where f, the original function, is concave up or concave down. Remember, concave up is like, looks like a cup, where you just fill it with water. Concave down looks like a hill, where you pour the water on it and runs off. And then we can find the points where the function f transitions between concave up and concave down. Those are called the inflection points, by looking at where the second derivative changes from positive to negative. So we kind of all packaged this together, and we'll use these ideas further in chapter 10 when we actually we look at these processes more in depth. In particular, the idea of finding these extrema is a really practical problem, because the extrema in a problem is essentially going to be the best or worst way of doing something, which is a really important question in, like, you know, economics or business or engineering, or, you know, a lot of different disciplines where you want to find, okay, what's the, you know, like, how do I design this part to maximize this output? Or how do I design this part so that it's as cheap as possible to make? Or uses the minimum amount of material? Or, you know, these are all very common real-world questions. All right. So let's look at some examples here where we can use this derivative to answer some questions. So it says, given the derivative f prime is equal to x squared minus x minus 12, it says to identify the intervals where the function is f is increasing or decreasing. So if I want to find out where f is increasing and decreasing, and I'm not given f at all, right? I have no idea what f looks like. I know what its derivative looks like. What I'm going to do is I'm going to have to use the derivative, right? So I'm going to use the idea that, okay, well, I know that where the derivative is positive, f is increasing, and where the derivative is negative means f is decreasing. So I'm going to use the derivative as a proxy to find these intervals for f. So if I want to find out where the derivative is positive and negative, basically what I'm going to be doing is building a sign diagram for that function. You guys remember building sign diagrams last year in pre-calculus? Okay, well let's do it anyways. So the first thing I want to do is I want to start by setting our derivative equal to 0. Because as long as this is a continuous function, which it is, how do I know this is continuous? It's a polynomial. All polynomials are continuous. So since my function is a polynomial, I know it's continuous everywhere. So the only way for a function that's continuous to transition from positive to negative or negative to positive is it has to cross the x-axis, which is what we're finding here, the points where the graph crosses the x-axis. So what type of an equation is x squared minus x minus 12? We call that kind of an equation. Polynomial, correct, but more specifically, what type of polynomial?
Quadratic.
Quadratic. What are the different methods I have for solving a quadratic?
The quadratic equation formula.
Quadratic formula. What else? Factoring. What else?
You like solving for, I forgot the name of it, like solving for b squared or whatever.
That's like the quadratic formula still. Graphing would be the other one, right? I could graph it on my calculator to find the x-intercepts. For this particular problem, which one would be the most efficient method to choose? Factoring, right? Since the leading coefficient is 1, typically factoring is going to be the easiest. This should be a very easy factoring problem. We just need to find the two numbers that multiply to give us negative 12 and add to give us negative 1. Those two numbers are?
-4 and 3.
Good. So my x-intercepts are at 4 and negative 3, right? It's okay? So I'm going to go ahead and draw like a number line. On this number line, I'm going to add the numbers negative 3 and positive 4. I want to make sure I'm adding them in a sensible place, i.e. that negative 3 is to the left of positive 4 because that's still related on a number line. Of course, Mr. Kulik. And now what I'm going to do is I'm going to pick a test, or what that does is that separates the number line into 3 intervals, right? So the stuff less than negative 3, the stuff between negative 3 and 4, and the stuff bigger than 4. Ready to see that? I'm going to pick a test value of x from each of those 3 intervals. It does not matter the test value, but like, come on guys, don't pick something like that's going to be a pain in the neck to deal with. So I'm picked negative 4 and 0 and 5. Okay? I mean, you could pick like 2.7854321, but like, why? You know, like you're just kind of a masochist. And then what I'm going to do is I'm going to see what happens with the derivative at those values. Now, all I really care about is whether the derivative is positive or negative, correct? I don't actually care what the number is. So I'm going to do this in kind of like a hand-wavy sort of way. I'm going to look at the factored form. When I plug negative 4 in, I get a negative times a negative, which means that f prime of negative 4 is positive, right? Negative times negative is positive. Is everybody okay with the reasoning that I did there? Now, could you plug the number all the way in and get the actual value of f prime of negative 4? Sure, if you want, that's fine. All I need is the sign, though, so I'm not going to bother with all that. I'm just going to look at the factored form and just, is it negative times negative or positive times, you know, like, keep it simple. I'm going to do the same thing now with 0. So I plug 0 into x minus 4, I get negative into x plus 3, I get positive. Negative times positive is? Oh, you guys are on it today. Wow! And then the last section, I'm going to plug the 5 in. 5 minus 4 is positive. 5 plus 3 is positive. Positive times positive is? Positive. Okay. So what did I see here? I see that the interval from negative infinity to negative 3 is increasing. The interval from negative 3 to 4 is decreasing. And the interval from 4 to positive infinity is increasing. Because the derivative in those sections has to be positive, negative, positive, respectively. So I would say then my answer, I would say we're increasing and decreasing. I'm just kind of formulating that together into interval notation and just labeling my answer. Do you guys remember sign diagrams now after I drew it? Yeah, right? Like you did this in pre-calculus. Standard way to like solve inequalities, right? It's a nice skill that we're just repackaging here and making it a a calculus technique. All right. So just as an aside, the question does not ask this. So at negative 3, the graph f is going increasing and then changes to decreasing. What is happening at negative 3 then? The graph goes to increasing and then changes to decreasing.
Inflection.
It is a maximum, right? It attains a local or global or absolute maximum. We don't know whether it's local or absolute yet. We'd have to do more analysis there, but it's at least a local maximum. At 4, the graph is going decreasing and then changes to increasing. What happens at 4? Decreasing to increasing. That makes a minimum, right? Do I know if it's local or absolute? I don't. It's at least a local, though. We don't know if it's the highest overall point or not without doing some further analysis. We'll talk about that more in chapter 10. But I just want to point this out that, like, just from what we've done right here, we can already identify extrema, right? Just by looking at our sign diagram. Next example says, the rate of change in a population is given by the function dp dt equals 4 over t plus 1, where p is the population in thousands and t is the time in years for t greater than or equal to 0. Find the initial rate of change in the population. So when I see rate of change, that's looking for a value of, or a value for dp dt. Right? Rate of change is a derivative. I hear that in a question. I'm looking for a derivative. So the derivative dp dt requires us to input a value for t in order to get that rate, correct? So what value of t does initial mean? 0. So the way we would write this, if I write our derivative this way, kind of so it looks like a fraction, I'm going to plug a value into it. I draw a vertical line and then write in the subscript the value that I'm plugging in. So that's just the notation. It means, it's like the same thing as like f of 0, that's how we write it when it's like dp dt, we draw the vertical line and write like t equals 0 down there. It's like the same thing saying like f prime of 0. It's just how the notation works, or how we use the notation. It means the same thing. Okay, so we get 4 as our output. Is that the answer? The IB loves to do this. Read the whole question. P is the population in thousands, and T is time in years. So what should my actual answer be?
3,000.
Yeah, 4,000 like units per year, right? Should have a, you don't know if the population is people or viruses or like, items in the factory or I don't know, whatever. So I just called it units. Does everybody feel okay there? Okay. So part B says, describe how the population changes over time. So what I'm going to do is I want to look at how, like I want to describe what P would look like, the graph of P. Now the only tool I have is its derivative, right? So maybe I go and try to do the same thing we did before and make like a sign diagram and figure out when population is shrinking and growing, right? That's reasonable. So I'm going to take my derivative and set it equal to 0 to solve, because I'm going to try to build a sign diagram here. How do I solve the equation 4 over t plus 1 equals 0? Nope. Nope.
No.
How do I solve an equation where the variable's in the denominator of a fraction? Multiply by what? I'm sorry, what? You mumbled something, Emerson. Multiply by. I wouldn't do the reciprocal.
But like it's one.
When you say the same thing, what do you mean?
Like t plus 1 over t plus 1. Yeah. Oh.
T plus 1.
T plus 1.
Multiply both sides by t plus 1. That's reasonable. So when you do that, we get 4 equals 0. What's that mean? Did we make a mistake?
No, the limit does not exist.
There's no limit here. But you're on the right track. What does it mean? We got 4 equals 0. Is that true? No. What is that telling us then? What's the value of t that makes that fraction equal to 0?
T can't be 0.
Just there is no solution to that equation. There's no value of t that's going to make that fraction become 0. Which should make sense. If I have a fraction, when is a fraction equal to 0? When the numerator is 0 and the denominator is not, right? Can the numerator ever be 0 here? No. What is the numerator? 4. Is 4 ever equal to 0? No. Okay. So no surprise, that fraction can't become 0. What is that telling us then? So that tells us that dp dt is either always greater than 0 or always less than 0, correct? If it never crosses the x-axis, it has to be one or the other. Everybody agree? I already know the answer. We've already done enough to tell us which one it is. dp/dt of 0 is 4. Okay. So if it's either always positive or always negative, and we had it positive once here, we know it's always positive. You know, everything else has to be, it's always positive situation, right? So the population is always growing. Everybody's okay with that reasoning? Now, we can do a little bit better than that though, because we can talk about how fast it's growing. Right? So, what I want to talk about is, as time goes on, is the rate at which the population growing consistently getting, is it growing faster and faster and faster and faster? Or is it like leveling off and we're hitting like a place where basically the population is going to be static and not changing anymore?
That depends on the way the graph looks.
So what we're talking about is really just what is the limit as t goes to infinity, as time goes on and on and on, what's happening to that rate of population change? So let's think about this. So when t equaled 0, we had 4, right? When t equals, say, 9, what are we going to get?
4/10.
4 over 10, or 0.4, right?
Oh,
If t equals 999,
very small.
we have 4 over 1,000, so 0.004. What's happening as t is getting bigger and bigger and bigger?
So that went on.
The population, the rate of population change is approaching what value?
0.
0. So the way I would phrase this is, population is always growing. However, as time goes on, the rate at which that population is growing is slowing and approaching 0. Does that feel like a good description here? Now, do you think this is common in like a biological population? That as the population is growing, eventually it levels off and we just kind of hit a stable population. Biology students? What do you think? Is this common? Yes, this is pretty standard behavior in looking at populations of organisms. What happens is you reach a carrying capacity, you create a population that's so large that basically all the available resources are being consumed and the population has no room to grow. That you're going to be losing members of your population as quickly as you're having new ones formed because there's not enough space or food or water or, in the case of like a plant, like ground to grow in or sunlight because the trees have all blocked it out for the young trees. Very common situation. This same situation exists not just macroscopically, but also like intracellularly when you talk about like epidemiology, when you talk about diseases. So the disease in your body also kind of functions the same way. It'll grow very fast, It'll reach a carrying capacity where it's basically infected all the available cells, and then no more growth is gonna, growth is gonna happen, or if you're talking about, population, you've infected, basically the limit in the population that's susceptible to being infected. That upper bound there is called a carrying capacity. Most population curves are what we call a logistic function. You guys remember that from pre-calculus? The logistic function looks like kind of like an S shape, where it has a horizontal asymptote at the lower bound and a horizontal asymptote at the upper bound. Typically in a population model, the lower bound is 0, and the upper bound we call the carrying capacity for the population. So these types of models using these derivatives, super important to other branches outside of mathematics, right? You can see that in a biological setting, this is something talking about population, being able to model population would be extremely useful, right? Whether you're in, infectious disease, or you're talking about conservation, or you're talking about, any other other things that I don't think of because I'm not a practicing biologist, but you can see where I'm going with this, right? Okay. Next example says the graph of the derivative is shown below. Write down the intervals where y is increasing and the intervals where y is decreasing. So again, when I say intervals where y is increasing and where y is decreasing, I'm just looking for where the derivative is positive and where the derivative is negative. So the place where the derivative is above the x-axis, that's where the derivative is positive, so that's where our function is increasing. And the spots that are below the x-axis, well, that's where the derivative is negative, so that's where the function is decreasing. So we'd say y is increasing from a to b, or from c to d, or from e to positive infinity. And then we can say y is decreasing then from negative infinity to a, and then from b to c, and then from d to e. Feel pretty good here? Fairly easy, right? Easier than the first example because they gave us the graph, there's no algebra to have to deal with, right? I just looked at the picture. I'm just looking at where the derivative is above or below the x-axis. Does everybody feel okay here? Okay. Power rule stuff we already did. I'm going to skate through all of this. I'm going to look at a couple of these examples here. So it says, for each function, find the derivative and then compute the slope of the graph of the function at the indicated point. Okay, so our function 3x squared minus 4x, what's the derivative? Part 1 is to find the derivative of 3x squared minus 4x. We've done this 2 days in a row. Practice how to do these derivatives.
6x minus 4x.
Close. 6x minus 4. So remember the rule. you can distribute the derivative across the addition and subtraction. So I can look at each term separately. Derivative of 3x squared, separate. Derivative of 4x, separate. I can pull the coefficients to the front. So I can look at 3 times the derivative of x squared and 4 times the derivative of x. Then I can use my power property. For the power rule for derivatives, the exponent becomes the new coefficient, and then we subtract 1 from the exponent. So the derivative of x squared becomes 2x, and then with the 3 out front, it means 3 times 2x, 6x. The derivative of x, the coefficient becomes 1. In the exponent, I have 1 minus 1, which is 0. X to the 0 is 1. So derivative of x just becomes 1. We have the times 4 in front, so I have minus 4. Part 2 then says, compute the slope of the graph of the function at the indicated point. So I'm just going to be plugging 0 in, because that's the x value, right? That's all I need. I'm done. Does everybody feel okay here? Did you know you can do this on your calculator too? Ooh. If you have your graphing calculator with you, I invite you to take it out to follow along. If you'd rather just sit and watch, that's okay too. I have calculators on my desk if you want to borrow one. Totally fine.
What's the half 9? No.
Yeah. 3x squared minus 4x. So this is our first function, right? Our function we're working on, yes? So if I graph this, here's the graph of the function. And if I press second and the trace button, which one of these commands looks like the derivative? 6, right? Where it says dy dx, that looks like our derivative notation. I'm at the point 0, 0 automatically. I press enter, it tells me the derivative is -4. Boom. Now, this is kind of a pain in the tuchus because I have to use the trace function to increment along to get to the point I'm looking for. If it didn't start me at 0, 0, this is not very appealing. Not the preferred way I like to do this, but it works. Can I show you another? Okay. So the other way that we can do this is from the home screen here. So back to the main screen, I'm going to press the math button. The command I'm going to choose here is called nderive. That's command 8. So that gives me like that dd notation for take the derivative of. So I'm going to put an x here for ddx. And I'll type in 3x squared minus 4x. And the value of x that I want to plug into my derivative was 0. So that goes there. I press enter and then boom, -4. Everybody's okay? Now, your calculator can effectively check the part 2 of this, right? The actual value. What it doesn't do is it will not give you the equation for the derivative. Can't do that. But what it can do is it can help you check your answer. Let's do that. Yes? So I'm going to turn off the graph of the 3x squared minus 4x. We said our answer was 6x minus 4, right? I'm going to have the calculator graph the derivative of y1. It can do that. It can't give me the equation, but it can give me the graph. And I'm going to graph these on the same axis and make sure I get the same line. So to graph the derivative of 3x squared minus 4x, I'm going to press math. I'm going to pick the nderive. ddx. 3x squared minus 4x. And then where it says x equals, put an x there. That'll treat it as like a function now because there's a variable in it. And now if I hit graph, the red line was our answer, the black line is the calculator's answer. Notice they have the exact same graph, which is good evidence that, hey, we did that right. Does that feel okay? Could you use this to check your answers on this take-home quiz I'm about to give you? Yes. Please practice that. It's great practice. Hopefully nobody gets any wrong because you're able to check them this way with your calculator. Oos. Good practice. All right. Done with that stuff. Next question says, find the coordinates of any points on the graph of the function where the slope is equal to the given value. If it asks me to find a place on a function with a slope, what am I going to need to use? The derivative. We're talking about the slope, right? The derivative gives me the slope of the function at a point. Gee willikers, Anthony. What's the derivative of x squared minus 3x?
2x plus 3.
Good. And I want to find out when this derivative is equal to 3, the slope. So I get one answer, x equals 0. Am I done? No, what does it ask for? Asks for coordinates. I have the x, I need to find the y now. Where do I get the y coordinate from? I have an equation that starts y equals, right? That's going to be the y coordinate. So I just plug 0 into the original function. I get 0, so my point is 0, 0. Everybody feel okay with that? It's not a very good comma, Mr. Kulik. All right. Next example says the slope of the curve y equals x squared plus ax plus b, where a and b are real numbers, and we're talking about at the point of 2, -4. The slope there is -1. Find the value of a and the value of b. Notice that we're given a slope, correct? At a specific point, correct? That basically is saying that y prime of 2 is -1. Everybody's okay with that? That looks like an equation. Let's start by writing that equation so we can try to solve for either a or b, or at least create a system of two, one equation for a system or something. So what's the derivative of y?
2x plus a.
2x plus a. So 2x plus a, okay. And so if I take this, I have 2 times 2 plus a equals -1. Is everybody okay with that? I just plug the 2 in for x. So a equals -5. Woo! Halfway done. Am I going to be able to use the derivative to find b? No, why not?
Oh, because there is no b 0.
B's not in there, right? Like there's no b. I can't. The derivative is useless to me. What still has b in it? This guy. Yes. So let's go ahead and do that. I'm going to plug the -5 in for a. Now I need to find like an x and a y to put in for that so I can solve for b, right? Do I have an x and y?
Yes.
Yeah, I sure do, right? Here's my x and y. So what I have here, 4 minus 10 is negative 6. And then I add that over and I get b is 2 or something. That look good to you guys? We're done. How'd that go? It's okay. Notice I started with the derivative here rather than the original. If you start with the original, you have both a and b in it. There's not much you can do with that because it has 2 variables. I want to start with the derivative where there's only 1 variable, because when you take the derivative of a constant, the b in this case, it just whoop, vanishes and becomes 0. Last example. Find the equation of the line tangent to the curve f of x equals 3x squared minus 6x plus 7 at x equals 1. If I want the equation of a line, what information do I need in order to write the equation for a line?
Slope and y-intercept.
Slope and y-intercept, or what else could I have?
Just like coordinates, maybe instead of coordinates and slope.
Okay, 2 points, or slope and a point, right? Those are basically the 3 situations. The one that we are going to be able to get is that one. We have enough information to get that one. Okay? So, how are we going to get the slope?
Derivative.
The derivative, okay? So I know that since we're at x equals 1, I just need the derivative of f at x equals 1. That should be my slope. What's the derivative of f?
6x minus 6.
Fantastic. So this is going to be 0 for my slope. Everybody feel good? How am I going to get the point then? I have the x coordinate, right? How am I going to come up with that y? Who's f? Right? Doesn't y equal f of x? So y should equal f of 1. So what I have there, 4. So my point is 1/4. I have a point and a slope. Which equation for a line should I use?
Point slope.
Point slope.
Yay.
Or when I simplify it down, I just get y equals 4. Not surprising, since the slope was 0, I have a horizontal line, right? Gosh. Just to visualize what just happened here, I'm going to graph this. 2 things on my calculator. All right, so we had 3x squared minus 6x. What was the plus 7 or something? What was the end? What was plus 7? Thanks, Katie. Okay. And we have y equals 4. And I'm going to plot that point 1, 4 also, so we can see the point that everything is passing through. So to do that, I'm gonna go and do stat, edit, and I'm just gonna put in 1.14. I'll turn plot 1 on so that graphs it. So the blue is the curve, the square is the point, and the red is the line tangent to the curve at that point. That's what the situation would look like. So that's what you did. Notice that the tangent line hits the curve in its local neighborhood in exactly one spot. But that's the idea. How do you guys feel? It's okay? At this point, you guys should be able to do all of the homeworks in chapter 9. I would say for Sunday, you guys should have 9.1 and 9.2 done. We'll save 9.3 and 9.4 for next Sunday. Particularly since you have this homework or this take-home quiz to deal with also over the weekend. You should have this done and ready to pass back to me when you guys return. So your next class, you should have your completed homework quiz ready to turn in. Everybody got a copy? Anybody have a question? Who feels pretty good? All right. Be done.